Welcome to Breadboarding. This is video 13 in the 8088 Breadboard PC series, and in this video we'll be looking at how to build and design a monochrome display adapter compatible with IBM PCs and MS-DOS. So in our plan, in the previous video, we completed the serial port and update in the monitor to be able to load and save data from the PC in the S-Record file format. And in this video, I'm going to be looking at the plans for the monochrome display adapter video controller. And I will include links at the top of the screen here and in the description for the whole series on developing graphics video controller for the original Nanocomp as well, for those that want to jump ahead and see what some of the things we're going to be looking at. So the video controller is a key part of what we need to be able to build out our basic floppy disk PC. And so once we've done the MDA card and the PS2 keyboard, then we really should then start to be able to get towards getting a breadboard PC capable of booting MS-DOS from floppy disk. So why use a monochrome display adapter rather than some of the other ones such as CGA, EGA or even VGA? Well, we need PC compatibility for standard PC software to work. The original Nanocomp 6809 video controller produced VGA output but was not PC register compatible. So the monochrome display adapter is simpler to develop, and also using dual port video RAM will reduce the chip count quite a bit. The EGA and VGA video cards use custom very large scale integration chips for all the control registers, and these were like 144 pins to 160 pins and not really suitable for breadboards. One of the other key things about the MDA is that it can coexist with other video cards for debugging. So if we're developing a CGA card, for example, in the future, it would allow us to have both the MDA and the CGA card in the computer at the same time. So this is a high resolution image of one of the very early MDA cards, and the original monochrome display adapter also included a printer port as well. Now you can see here we've got the Motorola 6845 cathode ray tube controller chip, and there's also the character ROM. Then we have, I think, 82114 1K by 4-bit RAMs. So the 4K and RAM came with 8 chips here, and then there's 56 other TTL logic chips, so 66 chips in total. So this was a full-length card. We'll hopefully be able to develop this in slightly fewer chips by simplifying the design somewhat. So I do plan to develop a CGA or a multicolour graphics adapter. It's a slightly extended version in later stages of the project, but I wanted to start simple first with a monochrome display adapter. The MDA has hard-coded ROM-based fonts and 4K of video RAM, so it's quite a bit simpler than some of the other designs. I'm not going to bother with a parallel port, although I will be making use of some of the VGA video digital analog converter palette chips that I used in later stages of the original Nanocomp 6809 design, because this just makes it much easier to deal with output to LCD monitors. A little known fact as well was that although known as a monochrome display adapter, it could in fact do to 16 colours with some versions of the card with an appropriate monitor. And this site here has quite a bit of information. I'll include this in the description below. According to the programmer's guide and PS2 video systems, the IBM MDA cards included support for colour monitors, and when we go through the design we'll see that there are colour signals could be made available. So what I'll do is focus on getting the monochrome compatibility first, but it'll be interesting to see if we can get the colours working with this as well. So the display is going to be 80 columns by 25 rows, and this allows for 1 byte for the character details and 1 byte for attributes or colour information, so a total of 4,000 bytes. Now the original MDA had 720 pixels along each line of 350 lines, so this meant that the characters were 9 pixels wide and 14 high, and this meant that the monochrome monitor would run at 50 Hz refresh rate and 18 kHz horizontal sync. Now those aren't available without getting little legacy CRT tubes, which will be difficult to get hold of. So I'm going to simplify this by making this work with modern VGA LCD monitors. I'm going to drop the 9 pixel wide characters and make them 8 by 16 like VGA. And in order to make this VGA output compatible, we're going to base this on 640 pixels by 400 lines. And this basically means we have 8 by 16 characters at 70 Hz and a 31.5 kHz horizontal refresh frequency, which are standard VGA signals. So I should now just take a look at the original IBM documentation. One of the reasons for the IBM PC success, I believe, was the documentation provided with the early versions provided great levels of detail, and you could even recreate the PC and things like this display adapter using the information provided. So I'll quickly just take through some of the key highlights of this. So it says it's 80 characters by 25 lines, and the IBM documentation talk about pels rather than pixels. There is a diagram here that we'll come back to when we talk a look at the design. These are the CRTC 6845 registers that it uses, so some of the values which are in here. We'll need to modify these slightly because we'll be running at different frequencies for VGA compatibility. Then the even video addresses had the character code and allowed for up to 256 characters. And then the odd byte was the attribute, and this included whether or not was blinking, the background red, green, blue, then the foreground red, green, blue, and then an intensity. There was an additional register that you could disable blinking, and this then became an intensity. And this is very similar to the attributes that were used in the Monochrome 6809 VGA compatible cards. So we'll make use of that. There is a slightly odd thing in that the 001 value, it enables underline on characters, which is not something you can do in VGA upwards. You can see here that underline is identified as this one. Then as far as the I/O ports are concerned, so we will be switching the Monochrome design to use Intel I/O ports rather than the current memory mapped I/O that I did to maintain compatibility with the original Monochrome design. The I/O registers will be used for accessing the 6845 control registers and some of these other status and control ports. So the control port has a number of things to enable blinking, disable blinking, to disable the video output. And there's also a rather weird one, which the high resolution mode always has to be set to 1. And the documentation warns of dire things will happen if you don't set this to 1 before doing anything. It could stop the system clock and cause it to crash. Now, in reality, this high resolution mode always has to be set to 1, so we'll probably ignore it for now. And then there is a status port to be able to tell whether the card is actually outputting any video at this point in time, and also the status of the horizontal line sync. So this would allow us to check this to see whether or not the video was being updated on the screen to avoid video snow. So I'll skip the printer adapter, and the key thing that the IBM documentation included was the logic diagrams. So this included the detailed diagrams of exactly how the adapter worked, and we'll be going through this in a little bit of detail, but just to show the information that's available here. Some of these are for the parallel port, so we won't be bothering with those. But there's about 10 pages of diagrams, of which I think 1 or 2 of them are for the parallel port. So it's about 8 pages of diagrams we'll be needing to look at. So let's take a bit more of a look in detail at the 6845 details. Some of this is carried over from the first series of videos I did when developing the video card for the Monochrome 6809. So this is the diagram that was pulled out of the technical documentation from IBM. So you can see here that we've got 2K of memory for the characters, 2K for the attributes. There is a certain amount of memory address multiplexing and data gating, and some complexity around here which we can largely avoid by using dual port RAM. And then the output of this was latched at certain points and then was used to either drive the ROM character generator to determine what the individual pixels needed to be to output each character, and that was then driven by the row address or raster address output of the CRTC, determines which of the 16 rows of the character we're using, and then the shift register then serializes those dots to actually output to the video process logic that controls whether or not we show foreground, background, blinking, high intensity, all that sort of stuff, and then outputs to the monitor. And then the attributes are basically providing the information about whether we're using blinking, underline, reverse video type attributes. Now in Doing this, we're going to substantially simplify things because we can remove a lot of the multiplexing and data bus gating because we're going to use a 4K dual port RAM. This does make some of the timing a little more complicated because we have to clock the data into the character latch slightly earlier than the data that we're clocking into the latch for the attributes and also the shift register here. We're going to be using the Hitachi part, the HD68A45S. Now these Hitachi parts were capable of running at a higher frequency, so 3.7 megahertz character clock. So this would be capable of going up to 28-30 megahertz clock. And also included quite a useful feature that it's necessary for the cursor and the display enabled signals to be delayed by 1 or 2 clock cycles. This actually includes a register values in here where this can be configured in software. In the earlier versions of the card, we ended up having to put in additional hardware flip-flops to delay signals, so this will simplify things as well. And by using the video digital analog converter that we used in the other project, then this will allow us a bit more flexibility in defining the colours and things and adjust things a little bit more. When we come then to build out, to say, a CGA compatible, then we will need this as well for that. So let's take a bit more of a detailed look at the 6845 information. So why should we use the 6845? Well, this was a video controller chip that was used by Commodore PET, BBC Micros, and also the IBM MDA and CGA adapters. It was not used for EGA and VGA, they used custom chips. It's quite flexible and not as constrained as one of the other chips, the 6847 that was used in the Dragon 32 and the Tandy Color. That was quite a bit more limited. It's able to address 16K of RAM in characters with up to 32 rows, so in theory it could do up to 512 bytes RAM in total. And it's been designed for character-based video displays, but can be used for graphics, as we'll see with the CGA. Can work at over 3 megahertz character clock, and with a 25 megahertz VGA dot clock, that means we need about 3.1 megahertz for the character clock. The Hitachi chip will comfortably work up to 3.7 megahertz. The horizontal sync and vertical sync signals which are produced for the video display may need to be inverted, so I believe one needs to be inverted for the video modes we're using. We're not going to bother with the light pen. Now the VGA video standard itself was only introduced around 1987 when the PS2 range became. Now, the reason why we're using VGA rather than the early ones is that the earlier standard video monitors used TTL levels rather than analog levels. So the VGA standard uses analog red, green, blue signals between 0 and 0.7 volts. That's what gives us the ability to have a huge range of colours. There are TTL levels for the vertical sync and horizontal sync, and really VGA has replaced the older monitors, and although there are some retro YouTube channels that will restore these, there's little point in trying to use one of these monitors. It just makes things more complicated and won't interface to video capture cards, for example. So VGA included a 256 colour palette out of 262,000, whereas CGA only had 16, and I think EJ had a palette of 64. The fonts were either 9x16 or 8x16. They were basically used the same character generator chip. There was just a bit of logic to expand certain graphics characters, which we'll look at when we look at the MDA. And the well-known 15-pin sub-miniature D connector that we've got on the right-hand side here. So the key things we need here are the red, green, blue, horizontal sync, vertical sync, and then there's the appropriate ground signals for those. There are some other pins which can be used for communicating with the monitor, but we don't need to worry about that. Some useful VGA timing data. This is one of the sites that I looked at previously. We're going to be doing 640 by 400 at 70 Hertz. This tinyvga.com has some useful links for the key timings and things here. So the 6845, a little more detail, it has 2 addresses in the memory map or the I/O port map. So there's an address register where the register number is selected of one of 19 registers, and then there's the data register. Vertical sync gives us 1 frame per page, so this is normally at a 70 Hertz refresh rate. The horizontal sync basically gives us 1 output for every pixel row, so that's at about 31.5 kilohertz, about 31 microseconds per line. There is quite a good detailed explanation of cathode ray tubes and synchronization. The reason why the LCD monitors are doing this is to maintain compatibility with cathode ray tubes. And if you want to understand a bit more about how that worked with all the magnetic coils and electron guns and all that sort of stuff, then there's quite a good link there. All these links I'll include in the description below. There's also a site that we'll look at when we come to do the software for this, which provides a register timing utility that you put in the values and it will give you what the default register values should be. Now the memory address lines here select the video RAM addressing, and the row address or raster address select the line of the character that we're actually drawing at a particular point in time. The cursor and display enable signals. The cursor is used to determine when we put the cursor on the screen, and display enable basically blanks the video during the vertical sync and horizontal sync periods. If we don't do that, then most monitors won't actually be happy talking to the video card if we don't do that blanking. As I said previously, there was a skew setting to delay these two signals just by register setting. Now, in fact, on our particular design here, the CRTC MA0 is going to be mapped to the video address 1 because we're going to need twice the frequency of the character clock, in fact, there, because we need to switch video address 0 between 0 and 1 for every character cell to actually switch from the character RAM to the attribute values. So that's a little bit of complication by using a single dual port RAM. Okay, so I'm going to break the video at this point, and in the next video what we're going to be doing is looking at the original IBM MDA Adaptor schematics. I've reviewed those in quite a bit of detail and excluded all the bits we don't need to worry about, and then we'll consolidate that information down into a high-level block diagram and a KiCad schematic. So if you don't want to miss out on future videos, please hit subscribe, and if you can hit like, that just makes the videos available to a wider number of people. Thanks for watching.